dude, it's just a crazy thing. Like the way science has brought all these things to, to us in a way that,
Yeah,
we can understand. And I understand that, the one language that is universal is maths, because maths is the language of the universe. That's how
yeah,
you
yeah,
get the answers to everything, which is why scientific research is very crucial. When something can be proven scientifically, you have to take that the way it is. Most of the time, there are few instances when you shouldn't, but most of the time you should do that because the maths is what confirms it. The math is what proves that this is the case. You know what I mean?
yeah,
Yeah,
yeah. I
yeah,
mean, when physics was first formed, it was just words. People wanted hardcore proof, and then the physicists realized that they can use maths as a form of a language to actually prove what they mean. Look at your Newton's laws, your Einstein's theory of relativity. They used maths to prove what they said, and it was actually true.
yeah,
So maths is a really helpful tool to prove what we find out there in the universe. You know.
yeah. True. Yeah, it's insane. So based on that, and based on what we've just said, that you have to follow what science says. What do you think of the Big Bang Theory? Do you believe in it? Do you take it as a fact as an astrophysicist?
The Big Bang Theory is true, in my opinion.
Okay,
It's
and
true.
you,
I
you
mean,
you're a
it's
Christian,
true.
correct? Or are you atheist?
Now I'm a Christian. I'm also a Christian.
Okay, so it's not mutually exclusive. To believe in the Big
No,
Bang Theory, to believe in evolution is not exclusive to being a Christian. You can
Christian.
believe
No.
in both.
Yes, you can't believe in God. There's a lot of scientists and physicists who were Christian. It's just that they were so they were so inclusive. I mean, what do you call it? They were so like focused on their work. People thought that they did not believe. They had no religion.
Yeah,
But you don't have to be an atheist to believe that to believe evolution or in the Big Bang theory. No, you can be both. You can be a Christian and still believe in the Big Bang, or evolution.
yeah,
Because the evidence is there that the Big Bang happened. It's just that our technology isn't that advanced enough to create such conditions that happened in the Big Bang.
yeah,
We are close, but we're still not there.
yeah, yeah. Definitely, yeah. The simulations. It would be interesting to see
Mm-hmm.
the simulation of the Big Bang in its most true form, I guess, you know.
Yeah,
But
yeah,
basically, okay, just to clarify, you correct me where I'm wrong, but the Big Bang Theory is basically that a lot of people get it mistaken because you hear Big Bang and you assume it's a huge bang. But what
yeah.
happened was there was nothing except a tiny, what's the word? Energy. There was energy, correct? And then that energy started to spill over. And then once it started spilling over due to the photons, the energy was photons. A big part of the energy was photons, correct? And then
Yeah.
those photons were moving around. They were moving around, very quickly bouncing around. And then they spilled over. And as it spilled over, we had the development of different, well, firstly hydrogen, and then we
Mm-hmm.
got to helium. And once we had those two, that's when the materials of our universe started to form, because stars came from helium through nuclear fusion, through hydrogen through nuclear fusion, and
Mm-hmm.
from there everything started to develop because of that large amount of heat. You get the supernovas from the stars, which gave us even
Yeah.
more elements, thus resulting in planetismals, thus resulting in other stars, black holes, etc., etc., etc. Gold, elements in general. Correct. That's how everything
Yeah.
went down.
Something. Yeah. Yeah.
Yeah. Okay,
So
perfect.
in the moment the Big Bang happened, the particles that were most dominant after the Big Bang were deuterium and helium. Deuterium is an isotope of hydrogen. So
Yeah.
those were the two things that were in abundance. So now, once the universe started to cool down, those particles between deuterium and helium, they started forming molecules. Started forming molecules, and the ones that weren't able to form molecules, they what do you call it? They were left alone because there wasn't enough energy to bond with other molecules. So with the Big Bang, it all came down to that those small kind of like instances where there were collisions and particles were colliding all over, forming molecules. And as the temperature decreased, these molecules started forming heavier ones that could form your intermolecular gas clouds, which in which after that formed your solar systems, your galaxies, and then your stars, and then your planets.
Yeah.
So it happened fast. The Big Bang happened fast, and then as the temperature cooled down, it took very long to form such astronomical structures.
Yeah. 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 Definitely. And you know, it wasn't quick, but then it's one of those things where the further it went, the faster the other processes were. So in the beginning,
Yeah.
it was slow. It was slow to get like a lot of stars, but as time went by, stars were being produced
Mm-hmm.
at a faster rate than initially.
Yeah.
Correct?
Yeah. Yeah.
Yeah. And then thus, because these stars were being created, stars, you get different phases of stars. You get the stars that are in the hydrogen and helium phase. Usually,
Mm-hmm.
um, what's the word? You get different variations. You can from a star you can get a black hole. You can get dwarf
And
stars. You can get you know
yeah.
different variations of the stars. Main sequence stars. You can get neutron stars. You can get
Yeah.
different supernovas. It goes on and it goes on and it goes on, right? And
Yeah. And the stars that formed back then, like really long ago, those are your red giant stars, those really huge stars.
yeah,
Because back then it was possible, but now star that forms now, it won't be as huge. After we scientists have found out that our sun is relatively young, compared to the age of the universe.
yeah,
You know, but stars, as we think that when you take a telescope and look out into the out into space, you're actually looking back in time. You know,
yeah,
and what we find is that the stars back then, they had a relative short lifetime. Because they weren't as stable as stars as the younger stars of this age. So as time progressed, the molecules in the universe started to form much more stable stars. But as time progresses, as a star progresses in its lifetime, it undergoes different stages. First the red giant stage, and then after the red giant stage, it starts to collapse under its own gravity. But now, depending on the size, it will either become a black hole, a neutron star, or end up being a brown dwarf or a white dwarf. So those final kind of like outcomes of a star depends on how it was initially. If it was like, for example, our sun will end up being a neutron star, or yeah, a neutron star.
okay. So what are the
Yeah.
differences between a neutron star, a white dwarf, red dwarf, whatever dwarf, and a black hole?
So a white dwarf is a star that's left. Like a white dwarf is basically what's left of the star, which is its core. That's what a white dwarf is. And
Okay.
a white dwarf, the difference between a white dwarf and a brown dwarf is all because it all comes to its luminosity. Luminosity is the brightness of a star. So the brighter the star, the more then the bright stars are white dwarf stars, and then red dwarf or brown dwarf stars are less luminous stars. And then a neutron star is a star that's called is
Okay, wait,
that
before you go there, let me just break that down. So basically, like a star, right? You get a star,
yeah
this round ball, right? And then
yeah
what happens is it's making energy through nuclear fusion, right? So
yeah
that's when it's
yeah
going from hydrogen, and then the hydrogen, or what was the other name for it? The one that started with a D.
deuterium.
The deuterium, yeah. It then binds
Yeah.
together due to the immense heat, because usually they would
Mm.
repel, but then due to the immense heat, they are able to fuse and then form
Yeah.
helium, correct?
Yeah.
And
Yeah.
then this keeps happening, right? You get to the
Mm.
point where it can be oxygen, nitrogen, carbon, those things. But
Yeah.
with a,
So the last stage of the, I think it's silicon. Yeah, after
yeah,
silicon, and then the star will have a core of iron.
yeah,
And once it has an iron core, it'll burn off. It'll try to burn off that iron, and then after it succeeds by doing that, it'll start to collapse. And once it
yeah,
starts to collapse,
yeah,
its
and
initial mass will determine its fate. It's either being a red dwarf, white dwarf, neutron star, or a black hole.
okay.
You know.
And the reason why when it gets to the iron phase, it doesn't continue the process is due to the fact that iron is unable to sustain
Yeah.
the energy, it
Yeah.
cannot keep producing energy like the elements before.
Yeah.
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 So basically, what keeps happening is when you have the core, you get a shell around that core. So you have a helium core, you get the shell, you know, the shell of energy that it's pushing out, right? So when it
Yeah.
gets to
Yeah.
helium, it's now pushing out the hydrogen energy, right, as it cools
Yes.
off, because the shell is going to be cooler than the core. So that's what keeps
Yeah.
happening the whole time until we get to
Yeah.
that phase of where
The
it's
iron.
iron.
It
Yeah,
has an iron core. Yeah. Yeah.
yeah. Okay, so then now the neutron star. How do we get to
So
neutron
basic.
star?
So once a star collapses now,
Yeah,
it undergoes a series of processes. So for a neutron star, if the sun's gravity or the star's gravity cannot overcome this neutron degeneracy pressure, the star ends up being a neutron star, meaning that it will be filled with neutrons in its core, and it will just keep on radiating energy. But now, if the neutron degeneracy pressure is overcome by the sun's gravitational collapse, that's when the star will become a black hole. But that usually happens with high mass stars,
yeah.
from 3 solar masses and upwards. Those kinds of stars are the ones that usually become black holes.
So basically, the neutron star would have gravity so immense that
Yeah,
the mass collapses into itself. So the gravity must be stronger than the radiation.
yeah, yeah.